Okay, welcome back to our second set of video notes. Today we are going to focus on graphing. In the first two videos, we really focused on the basics. What is position? What are speed and velocity? What is acceleration? What is distance? How are they related? We did a couple examples, and we also looked at some shortcuts that we'll be practicing. Today what we're going to look at is another way to examine and study motion, and that is by graphing. And in order to make accurate graphs, or to understand graphs, I should say, you really need to know, you need to have these two basic formulas memorized. And thankfully, they're things that you learned a long time ago. We're talking about how to calculate slope and how to calculate area. The formula for slope is as follows. If you want to calculate the slope of a line, you do that by taking 2 points on that line, subtracting their y-coordinates, and then dividing that by the difference between their x-coordinates. In other words, y2 minus y1 over x2 minus x1. You might have heard of this in the past as delta y over delta x or some sort of thing. A lot of times when I ask this question, people give me this equation instead. This is the slope formula right here. And I say you should memorize this, but you should have this, you should already have it memorized. Let me put it that way. Sometimes I get this when I ask what's the slope equation. I get this, y equals mx plus b. And I understand why people say that. This is not the slope equation. This, however, is related. It is the general equation for a line. Okay? Any line can be described by an equation of this general form. Y and x are your variables. M is your slope. And b is your y-intercept. Okay, so that's not the slope equation. This is. We're going to spend a lot of time trying to write or trying to figure out different slopes in this class, but we will also use this equation, but not for a little bit yet. Before, when you learned about slopes in math class, you probably never were asked what the units of the slope were. Okay, just like all the measurements, all the variables that we write down in equations have to have units, slopes have to have units in this class as well. You don't have to memorize any sort of fancy units for slope. All you have to do is memorize the basic pattern. The units of the slope are always going to be whatever your y units are over your x units. Y and x just referring to our different axes. Remember, y is the vertical axis, x is the horizontal axis. And that's exactly, so basically just whatever the units are up top divided by whatever the units are on the bottom. You might be wondering, okay, I learned how to calculate slope a long time ago, but no one ever explained why it's important. In physics, slope is very, very useful. It's useful for determining how the y variable changes due to changes in the x variable. If you remember from middle school science, your x variable, that's like your independent variable. You don't control that, okay? That's something that just, it's like time. Time is just going to keep going on. Your y variable, that's your dependent variable. That depends on the x variable, okay? An object's position might depend on how much time has passed since a certain starting point, okay? So slopes are useful for determining how that y variable changes as the x variable changes. That's why we study slope. We're also going to study area. You probably even looked at area before you looked at slope. You're only going to need to know two basic area formulas, and they're both very, very simple. You're going to need to know the area formula for a rectangle, which is base times height, and you're going to need to know the area formula for a triangle, which is not base times height, but 1/2 times base times height. Now, why do we study areas? In physics, calculating the area, and I'll show you what I mean by calculating the area in a second. It is useful only sometimes, actually. About 2/3 of the time it's useful, the other 1/3 it's not, for determining how a quantity has changed over time. So slope is for figuring out how the y variable changes specifically due to the x variable at a certain point in time. It's how the y variable is changing right now. Area can be used to find how something has changed over a long period of time. And notice I said just a quantity, not the x variable, not the y variable. It's usually something different than that. what we're going to do for the remainder of this video is we're going to take a look, and the video after this too, because I'm going to split this in two, we're going to take a look at the three basic types of kinematics graphs. We're going to take a look at position versus time graphs, velocity versus time graphs, and acceleration versus time graphs. Now, all of those are quantities that you should be familiar with, but each of their graphs is different and has slightly different tricks for reading them. Okay, the basic process is we're still going to be looking at slope and area for each of them, but for each graph, the slope and area has a different meaning. So you've really got to get good at identifying, first of all, before you even try to calculate a slope, what is being graphed here? You have to slow down and say, what is on my y-axis, what is on my x-axis? And to help you to understand what the different types of to help you to break down the different types of graphs, I've got 3 questions, basically a little procedure for you to undergo that you should always be asking yourself in your head at the very least the first time that you see a graph. So I'm going to write these up here. So these are the 3 questions to always ask about a graph. Okay? This is a little procedure that you should be following. The first question that you should be asking yourself, and it doesn't matter what the graph is of, is the y variable positive or negative? That's the very first question you should be asking yourself. Is the y variable going to be positive or is it going to be negative? And what is it over the whole course of the data that is being displayed? Sometimes it might be both. Sometimes maybe it'll start positive, become negative. Sometimes it might be just negative. Sometimes it might be just positive. The second question that you're going to ask yourself is the y variable going up or going down? Is it increasing or decreasing? You'll see in a second that this question is equivalent to asking, is the slope positive or negative? And the third question I always want you to ask first time you see a graph when you're starting to do your analysis of it is as follows. Is the slope getting more or less steep? Remember, one of the things that slope tells you is that, well, here's a science definition, useful for determining how the y variable changes due to changes in the x variable. Let's take that down a couple notches. When you first learned about slope, it was so you could determine how steep a line is. Okay? Think about like going up a hill or climbing a mountain. If the slope is very steep, you're going like straight up the side of the mountain. If it's very gradual, it's a lot easier to walk on. Okay, so 3 questions to always ask about a graph. The last one is the slope becoming more or less steep? I'm going to box that in. With those 3 questions, let's start taking a look at our first graph here. It's an x versus t graph. That means position versus time. It says displacement over here. I really should have wrote position. You can cross this off and you can write position here. Okay, still measured in meters. And you can tell from our position versus time graph that, well, actually, let's just start applying, well, I take it back. Let's not apply the questions just yet. Let's do some basic slope and area calculations just to kind of get our feet wet. So the slope, remember, we can't take a slope yet. We need to draw in our best fit line. You learned how to do this in math class. Now this is a really easy best fit line to draw because these points are directly on a line. So what I'm going to do is I'm going to take a straight edge. Doesn't have to be a ruler. You can just take another piece of paper. And I'm going to draw my line of best fit. Again, I designed this so that these points perfectly fall on a line. Normally, real data would not fall perfectly on a line like that. So our slope we get by taking 2 points that are directly on this line of best fit that I just traced, and we plug them into the slope equation up here. And again, I'm always going to write my equation first. So y2 minus y1 over x2 minus x1. If you don't do that, it will be points off. So I need to pick 2 points. If you've got a perfect set of data like this, I usually like to pick 2 points that are kind of far away from each other, but it doesn't matter. I'm going to pick this point right here and this point right here. The y-coordinates of these points. This point looks like it's at about 75 meters or so. This point down here, the other y-coordinate looks like it's at about 5. So we're going to do 75 meters minus 5 meters. And the x-coordinates, remember that's down here, The 75 meter point is at 10 seconds. This is 0 seconds. So we do the calculations real quick. 75 minus 5 is 70. 10 minus 0 is 10. 70 divided by 10 is 7. And the units of that slope are the y units divided by the x units. The y units are meters, that's the units on the y-axis, divided by seconds. So this is meters per second. I'll say more about that later. We'll talk about what that slope represents. Let's find the area real quick, though. Now, here's what I mean by area, because this is going to be a little bit weird. What I mean by find the area of a graph is we want to find the area between the line of best fit and the x-axis. That is all this area right here. Not this, because there's no x-axis up here. It's this line up to the line of best fit. Okay? And you can see that this shape is generally triangle shaped, but actually it doesn't quite go all the way down to 0. It's actually a trapezoid shape. But like I said, you'll never have to know the area formula for a trapezoid because all we need is we just need to split this up into triangles and rectangles. In this case, we can split up into one triangle and one rectangle. Watch what I do here. I'm just going to make a dotted line that goes across like this, and now I have a real skinny rectangle down on the bottom, and then a triangle up here. So if we're trying to find the area, I'm going to find the area of this little skinny rectangle, I'm going to find the area of this triangle, and then we're going to put them together. If you're not quite sure why we're doing this yet, that's fine. Just hold on. The area of the little skinny rectangle. Remember, the rectangle formula, the area of a rectangle formula is base times height. The base of this rectangle, you can see, goes from 0 to 10, and the units are seconds. Even area units, this base and height, even those get units. So the base is what I say, 10 seconds. The height, since this little triangle, since the big triangle seems to start at about 5, well, that means that the height of the rectangle is 5 along this axis. We're not actually measuring in centimeters how big this rectangle is. We're using the axes of the graph to figure out its size. So 10 seconds times 5 meters equals 50 meter seconds. Okay, meter seconds, that's a weird unit. Now let's find the area of the triangle. We know that the area formula is 1/2 base times height. So we do 1/2. The base of the triangle is, again, 10 seconds. The height of the triangle is definitely not 5 this time. It starts at 5 and goes all the way up to 75. That's a difference of 70, so the height of the triangle must be 70 meters. 1/2 times 10 is 5, times 70 is 350. And again, that's 350 meters times seconds. So the total area would be this. The area of the rectangle plus the area of the triangle, 50 meter seconds plus 350 meter seconds. The total area is 400 meter seconds. Okay, so we've made some basic calculations, the slope and the area. Now let's dig into actually answering those questions. Okay, so we can start to understand what is going on with this graph. The first question that we have to answer is number 1, is the y variable positive or negative? I'm going to answer them over here. Answer to question number 1. In this case, the y variable, which a little confusingly is x since we're talking about position. Matter of fact, I'll write position. The position is always positive. Okay? So the position is always positive. If we look at the little dots, we can see that that position is always positive because none of them are below the below the x-axis. Matter of fact, at 0 seconds, the position looks to be about 5 since the position is on the y-axis. Then after 1 second, it's a little bit above 10, maybe like 12. Then it's at about 20, and so on and so forth. The position continues to increase until we get to 75. It's always positive. Okay, so first question we already answered. Is the y variable positive or negative? In this case, it's always positive. Question number 2. Is the y variable increasing or decreasing? Is it going up or going down? And very obviously here, the y variable is increasing. The position is getting bigger. It starts at 5, then 12, then about 20, then about 27 or so, then about like 33, and it keeps going up until you get to 75. So we say that the position is increasing. Now look at what that means in terms of our best fit line. It means our line has a trend like this. And what do you notice about the slope of this line? It's positive. There's a relationship between if your y variable is increasing or decreasing and your slope is positive or negative. An increasing y variable means your slope is positive. A decreasing y variable means your slope is negative. We're asking the same exact question here. It's just two different ways of phrasing it. So we're going to say the position is positive or is increasing, so the slope is positive. Okay? Make sure you understand what slope means. Slope doesn't mean the individual points. The slope means the trend of the points, okay? The slope or steepness of that best fit line. Data points themselves don't have slopes. It's only the best fit line that has a slope. Now, the last question is the slope getting more or less steep? This is where we have some issues sometimes. A lot of people like to tell me that this slope is getting steeper. That means if you're climbing up this hillside, that means it's getting harder and harder to climb. It's getting more and more vertical to the point where you're like, got to bust out the rock climbing equipment. Is this really getting steeper? No. Is it getting less steep? No. This slope is the same steepness throughout. Slope has the same steepness throughout. Okay? So we've answered the questions. We see from this graph that the y variable, the position, is positive. It's always increasing, but the slope itself has the same steepness. That means that the y variable, the position, is increasing at the same rate the entire time. Okay? That's important. The position is increasing at the same rate the entire time. Imagine what sort of data could have led to this. This is just an object that is moving away from the origin, okay, in the positive direction at the same rate the entire time. What we're going to do now is we're going to come to some conclusions about this graph, which are really, really, really important. We're going to list them down here. These are going to be very important facts that you're going to remember, and they work for every single position versus time graph. The first conclusion actually relates to the first question. To know the position of an object on an x versus t graph, simply look at the y coordinates. This is almost too obvious to state, but sometimes once we really get into all these graphs, people forget this. If you want to know what the position of an object is and you have an x versus t graph, just look at the y coordinates, okay? At 6 seconds, this object is at like 48 meters, okay? It's as simple as that. Don't forget that. 2. This is one of the first big revelations of the course, and it's one of my favorite things to teach. We said that the y variable, the position, is increasing, and we said that the slope is positive. Well, we actually calculated the slope up here. It was 7 meters per second. And we know that that units for meters per second, okay, anytime you see meters per second, that's the units for velocity. So interestingly, since the slope is 7 meters per second, or since the slope, and meters per second is the units of velocity, we actually are seeing that the slope of an x versus t graph is equal to the average velocity of the object. Now that's really interesting. Let's let that sink in for a second. What that means is we found the average velocity of this object. We didn't even take velocity data. We just took a bunch of position data and some time data. We threw them on a graph and we actually found the average velocity. We didn't even have to use one of those kinematics equations we used a couple of videos ago. We got it literally just from the graph. Okay? The graph is just position and time data, but if we analyze it, it's actually so much more. This is super, super important. Okay? You need to put stars around this one. This is very, very important. There's 2 more conclusions that we can draw. Okay? So we've talked about how to know position. We've talked about how to find average velocity. Okay? Take the slope. We can also get a sense of what the acceleration is like. Okay? For this graph, we said that the slope had the same steepness throughout, okay? And since the slope is the velocity, what that implies is if the slope is the same throughout, then the velocity is the same throughout. That means the velocity doesn't change. Think back to the definition of acceleration. The definition of acceleration is the change in velocity over time. If your velocity doesn't change, guess what that means about your acceleration? There is none, okay? To describe acceleration on an x versus t graph, look at how the slope steepness changes. If it doesn't change, then the acceleration is 0, because that means the velocity is not changing. If it does change, if it gets steeper, that means that there is what we would say is a positive acceleration. If the slope gets less steep, then that means that there's a negative acceleration. And actually, as I say that, I realize that it's a little more complicated than that. Let's just leave it for right now as if the slope steepness changes, that means that the object is accelerating. One more conclusion. Let's go back here to this area. We said that it had units of meters times 400 meters times seconds. That's a junk unit. It doesn't mean anything. Area under curve is meaningless for x versus t graphs. Okay. So that's a basic summary of all the facts that you need to know about a position versus time graph and how to read it. If you want to know position, look at the y-coordinates. If you want to know the average velocity of the object, find the slope of the best fit line. If you want to describe if this object has acceleration or not, look and see if the steepness changes. Unfortunately, the area doesn't tell us anything. Okay? We're going to get lots of practice with position versus time graphs. We're also going to get a lot of practice with velocity versus time graphs. So let's do that now. We've got another graph. This is velocity versus time. You can see these graphs are not related at all, okay? First thing we need to do, again, let's calculate the slope and the area under the curve. So let's line this up. There we go. Okay, now this looks like it starts off at about, actually I'm not going to use those. Let's use some other data points. I don't know, let's use this one and this one. Okay, so to find the slope, we do y2 minus y1 over x2 minus x1. Make sure you get the points right. This is going to be my y2 and x2. So for y2, that looks like it's at about 19. And notice the units are going to be meters per second. So 19 meters per second minus, let's see, this is about 28 meters per second over 7 seconds and 4 seconds. Make sure you have the same coordinates for each. So if this is point 2, then you gotta use y2 and x2 right there. Don't flip-flop the order. Don't try and force it to be positive because this slope is not positive. 19 minus 28 is negative 9. 7 minus 4 is 3. Divide that by 3. We get a slope of negative 3 meters per second. And the units, I'm giving it away. Meters per second squared are the units. Real quick, let me just show you why. Remember, slope units are always y units divided by x units. This would be meters per second divided by seconds. You have a complex fraction here. If you have a complex fraction, I like to keep in mind, it's much easier to write a complex fraction if you write it as a series of multiplication of two fractions. This is the same as saying meters per second times 1 over seconds. Meters times 1 is meters. Seconds times seconds is seconds squared. The units are meters per second squared. The area, again, is going to look something like this. Okay, we have a little rectangle down here. We have a triangle up here. Area of the rectangle is base times height. The base is 10 seconds. The height is 10 meters per second. And 10 times 10 is 100. Now this time, seconds times meters per second. Look what's going to happen to those seconds. You have a seconds up top, seconds on the bottom. Just imagine you had like a variable up top and a variable on the bottom. They cancel out. You're left with the units of meters. So that's 100 meters, that area right there. For the triangle, 1/2 base times height. So we have 1/2, the base is 10 seconds. The height, this goes from 10 up to 40. That's a height of 30 meters per second. 1/2 times 10 is 5. 5 times 30 is 150. 150 meters. The total area is just the sum of these. Now remember, the area didn't mean anything up here. It was kind of meaningless. Down here, that's not going to be the case. We see that we have units that, at least they're units that we would measure things in. The total area is 250 meters. All right, so I'm running out of time on this video here. Let's at least answer the questions about the graph, the first 3 questions, then we'll get to the conclusions. So on our graph here, let's answer our question. So first question, is the y variable positive or negative? Remember, this is a velocity versus time graph. This is no longer position versus time. So when we talk about the y variable, we're talking about the velocity. So let's answer the questions. Is the y variable positive or negative? Look at all your y variables. Even though there's a decreasing trend here, don't get fooled. All of these data points are positive. They're all above the x-axis. So when we answer the question, is the y variable positive or negative? What we say is v is always positive. For this particular graph, you could have a graph where the velocity data points are below the y-axis. Okay, that's another type of graph you could have. But in this case, the velocity was always positive, which looks weird because you see this downward trend. What does that mean? Think about the second question. Second question says, is the y variable increasing or decreasing? Here we go. The y variable is definitely decreasing. The velocity is decreasing. Now, think about what that means. If the y variable is decreasing, if it's going down, look what that means the slope looks like. The slope has to be negative. So when we say the y variable, or the velocity is going down, the y variable is going down, that means that the slope is negative. And third, is the slope getting more or less steep? This is the same question that we had last time. The slope has the same steepness throughout. Okay, slope has the same steepness throughout. Real quick, let's get to those conclusions. These questions help us answer those conclusions. What we see is an object that always has positive velocity. Guess what that means? It's always moving forward, but the velocity is decreasing. Okay, so it's moving forward, but the velocity is getting smaller. This is an object that's coming to a stop. I know it sounds a little weird, but you've got it. We're going to work in this class to get to the point where you can look at this and say, that's an object that's getting slower. That's an object that's coming towards a stop. It's not all the way stopped. It's still moving after 10 seconds, but it's coming to a stop. Just because the graph ends doesn't mean the object stopped there. That's just the limit of our data. Here's our conclusions, or at least some of them. Conclusion number 1. Okay, how do we tell the velocity from a velocity versus time graph? Okay, to tell v on a v versus t graph, simply look at the y variables, the y coordinates. Okay, so after 2 seconds, this object was moving about 34 meters per second. That's it. All right, and in this case, we are going to, well, I guess I'll put this back up for this. The object is always moving forward. Forgot to say that when we were up there. Conclusion number 2. We said that the velocity is decreasing and the slope is negative. That makes sense because we said up here the slope was negative. We said it was -3, and we said the units were meters per second squared. We've dealt with those units already. Those are the units of acceleration. So since the slope is since we can measure the slope here, and the slope ends up with units of acceleration, well, what this tells us is that the slope of a v versus t graph equals the acceleration of the object. Okay, so in this case, this acceleration was negative. I've got two more conclusions, and then I've got two more conclusions, and then we will get to a. There's one more thing I want to show, and then we'll get to an A versus T graph in the next video.